This is Porterville College, Physics 104B, Chapter 19 homework. Number 13, we're using the formula that the Carnot efficiency, or the ideal efficiency, for a heat engine is 1 minus the ratio of the operating temperatures, T cold over T hot. So you plug in the various numbers. For part A, it's 273 over 373 Kelvin. Remember, these always need to be in Kelvin. Absolute temperatures, so that's 0.268. Part B, your temperatures are 277 Kelvin divided by 298 Kelvin, which is an efficiency of 0.0705. And part C, 293 Kelvin over 1273 Kelvin with an efficiency of 0.770. Oftentimes efficiency is expressed as a percentage, so multiply by 100 for that. 26.8%, 7.05%, and 77.0%. Number 15, we're looking for the cold operating temperature. We have efficiency, we have the hot operating temperature, 4.25 Kelvin. So going from our Carnot efficiency equation, we need to solve that algebraically. So I've taken this through 2 lines of algebra. You should get Tc equals Th times 1 minus E. 0.948 Kelvin is the answer. What this problem shows is that it's not necessarily the spread. I've emphasized in class that there's a difference in temperature, and the bigger the difference, the better. But actually, it's really not about the difference in temperature, it's the ratio in temperature. Here you have a very small difference in temperature, about something like 3 kelvins. But they are so different in ratio compared to each other that that's what makes it a high efficiency engine. Number 16. You have QH and W, so for part A, just use the efficiency equation. Efficiency for a heat engine is work over QH. You should get 0.389. Part B, how much heat is rejected in each cycle? So this is just conservation of energy. QC plus W equals QH. So the rejected heat is QC, QH minus W. So 900 minus 350 joules, so that's 550 joules. Part C, engine rejects heat at 10 degrees Celsius, so we can say Tc equals, let's convert that, 283 Kelvin. What is the high temperature, the maximum temperature? A little bit of algebra has Th equals, you can follow the algebra there. But it comes down to Th equals Tc over 1 minus E, which is 463 Kelvin. Let's convert that back to Celsius, 190 degrees Celsius. Number 26, a Carnot engine extracts, so we have QH is 890 joules, TH 550 Kelvin, rejects 470 joules to a cooler reservoir, so QC is 470 joules. During each cycle. And so later on we'll talk about the timing of that cycle. So the work done during each cycle, conservation of energy, work equals QH minus QC, that's 420 joules, 890 minus 470. The efficiency, W over QH, so 0.472. For part C, I showed the algebra back on the previous, or on problem 15. Tc equals Th times 1 minus E. So you can plug those in and get 290 Kelvin. Now for part D, power equals work divided by time, and we'll take that for one cycle. Well, the work for one cycle is 420 joules per cycle. We figured that out back in part A. Now, per time, it says there are 22 cycles per second, so the time of one cycle is 1 second divided by 22, 1 over 22 seconds per cycle. So 420, that becomes times 22, 9240 joules per second, or 9240 watts. Number 27, we have the maximum temperature, we have the cold reservoir temperature into the river during different seasons. So Tc for winter is 273 Kelvin, Tc for summer is 298 Kelvin. So we find the efficiency. We find it slightly more efficient during the winter time because of that colder operating temperature. E equals 1 minus Tc over Th. So for the winter, it's 0.521. For the summer, the efficiency is 0.477. For number 33, Tc is 273 Kelvin, 2H is 32 degrees Celsius, so that becomes 305 Kelvin. So the coefficient of performance of the refrigerator, Tc over Th minus Tc, is 8.53 for part A. For part B, coefficient of performance is Qc over W, so Qc equals W times the coefficient of performance. Now this next line, I wrote it in the symbolism of calculus, but we're not actually doing any derivatives. Putting it as a rate of time, I just wrote it dq over dt. So I took this line, Qc equals W times COP, and took the rate of time for those. So this becomes dQc dt equals dW dt times the coefficient of performance. So the dW dt, that's 12,000 watts, times the coefficient of performance, which we found in part A. I took it out more digits in what I got for part A, so 8.53125. And we get 102,375 joules per second. Now, question B is asking how much water can it freeze in 1 hour? So we want to now look at, we've just found the rate of heat extraction. Now we want to look at, in 1 hour, how much heat can it extract from the water. So it's going to be the rate of heat extraction times the time. There's the rate, 102,375 joules per second, times, we're talking about 1 hour, so 3,600 seconds. And we get that the total heat extracted from the water will be 3.686 times 10 to the 8th joules. Now we come over here, and we use the equation for the changing of phase. Q equals m times the heat of fusion for water, which means m, the mass, is the heat extracted divided by the heat of fusion for water. So 3.686 times 10 to the 8th joules divided by, you can look up in the table in the previous chapter, the heat of fusion for water, 334,000 joules per kilogram. So we get a mass of 1,100 kilograms. That is the end of Chapter 19 homework.